So I won't reiterate the slide, only to kind of get a little bit of introduction of where Poseidon is from an industry standpoint on the bottom. So it looks like Mark already kind of covered a little bit of that. But so just real quick, Stephen Steen, sales and marketing for Poseidon. I have been on the other side. I've been a customer of Poseidon, so I've used the sensors in the field for different type of pieces of equipment. I came from wind industry, which you can kind of see on that bottom left-hand corner. We've been in for quite a while. But we are in almost all industries where you have a large, oil lubricated pieces of equipment. So anything that has a large engine, large gearbox, hydraulic systems, we've touched a little bit of those, or we're kind of building in a little bit. So we've basically become a name brand within the wind industry. We are retrofitting thousands of wind turbine gearboxes per year with different operators and that sort of thing. We have gotten really heavy in mining, steel. We're getting into a lot of different manufacturing, oil and gas. We're doing quite a large number of deployments as well. So we're quite often down here in Houston. Now it's nice to have some folks down in Houston here as well, prior to what we have. So from basically an industry standpoint, any sort of fluid lubricated equipment, we're probably have some sort of installation in where we have some experience. And in other areas, we have larger deployments and a little bit more experience in that. So when it comes to the current Poseidon system, so Jeremy's going to go through the iAlert and potential combination of this. I'll just talk about the oil sensors and where they sit today. You will see on the bottom left-hand corner, we have done, as a partner to ITT, some integration of the vibration nodes themselves into our own gateway, which is this here in black. But effectively, we are providing a unique end-to-end hardware solution with cloud-based monitoring for online oil condition monitoring. I'm going to go through examples from each individual sensor, but unique in the market, you have some sensor manufacturers that make one or two or several different sensors that they sell. Ours are inherently better. They perform much better. We have some folks in here who can attest to that. They have basically overall better detection capabilities for what we are trying to measure with those sensors. And we have that unique perspective that we talked about before of being able to take that data that comes off the sensors and turn it into something useful. And I'll show you some examples of that, of what we're doing today. Whereas, again, a lot of the other sensor manufacturers, they're going to sell their sensors to an end integrator who integrates it into their solution, and that integrator becomes the expert on what that data looks like. Since we are monitoring so many different pieces of equipment in so many industries, we've now become also the ability to take that data and turn it into something useful, which we will continue to do with the the iAlert platform as we start to integrate that. So Poseidon Live, Jeremy will give you a little bit of a demo of that as well. So you'll get an idea of what that looks like. But that's our current platform where we're doing our analysis on these sensors. So a lot of you may be familiar with kind of the current state, which is lab sampling. So I probably assume most of you are looking at that. One thing I like to start out to make sure we differentiate a little bit is we are not fully replacing lab sampling in terms of the same detailed information you get from a lab sample is going to be coming from these sensors. In one case, the wear debris sensor, you're getting more quality data than you would from a lab sample. In other cases, with the oil quality sensor, which we'll go through, it's more of an alert trending tool. It's sensitive to the changes that you would be familiar with seeing in that lab analysis, but it's not necessarily giving you that same output you're used to. So we're not giving you a TAN, TBN, oxidation number, but the sensor is sensitive to it to see those changes, track and trend it over time. So you can use that from an operational standpoint to make decisions, and maybe based off of what the sensor is telling you, you may need to take a lab sample to determine what the problem is, but at least you know that that's occurring and you can take action on it. And again, I'll give you some of those examples. One I like to use is the difference between a lab sample versus an actual sensor. We get requests all the time saying, can you give me a sensor that gives me these 5 properties that I need to know? And every once in a while, one will sneak in. It's actually a chemical process at the lab where they take a little bit of that oil sample you gave them, mix it with something else, and they look at a color index to determine what the reading is. Well, that's not even an electrical reading that we can then turn into a sensor. That's a chemical process that they have to do. So we're not fully replacing what that is. We're trying to be sensitive to those things so that you can mostly take action, get ahead of it. Again, I'll give you some examples of that. But you may need to use, in some cases, a lab sample to get there. And this is just some example data. This is from an engine. Some of you guys may be running some engine applications, but this is tracking and showing TBN in relation to some lab data output from our sensor. So just look at kind of that blue line. Each one of those dots, because this is in a test lab, basically pulling a bunch of samples out. We've done a ton of testing. Ryan Brewer and team have been working on this for quite a while, looking at different ways of taking those measurements and comparing it to the lab data to make sure that it is correlating with those changes. So as TBN changes, we're going to see that in our data, but we're just not going to know what that exact number is. Same thing with oxidation and a lot of those other things.
So those sensors being utilized on the sump, full sump, or do y'all put them in line, like use them upstream, downstream with filters, that kind of thing?
Great question. Yep. Good question. So just to repeat for those online, kind of where are we installing these? Where are they at? So in some cases, they are going in the sump. The oil quality sensor certainly could be. It's not ideal because you don't get a lot of churn in that sump, and you're going to measure whatever's on the end of that sensor head. And so if it's in a location and that oil is not churning very much, you're going to get old oil, those sort of things. We get much better data if it does have like a filtration system. Certainly we would like to be in line. It also makes it easier to install because that lubrication system has more fittings and things that we can integrate into. The wear debris sensor has to have flow through it. And I'm actually going to go do that sensor next. So we have to have flow through it. So you have to either, it's a splash lubricated system, you'll add a pump to circulate it. If there's already a filtration system, we will integrate into that, maybe pull a small flow from it to take some fluid through, and we'll get a representative flow through that. So we, Tim Marvin and team, which you saw on that list, have done tons of installations on tons of different pieces of equipment. We have a lot of experience in that. So really what we need is a lubrication diagram and some photos. We pretty much can tell you how to do the install. It's fairly simple.
So this data came from being the sensor reading in line.
This was in line, yeah, that's right. Yep. On an engine.
I haven't done coolant or anything like that, have you?
No. Okay. Oh, coolant, yeah. Okay, I guess we've done some coolant. Okay. Certainly not predominant at the moment, but yeah. So showing the data from the previous one, that's the oil quality sensor. We'll go into some more detail of what that looks like. This is from the wear debris sensor, and I like to show this one is this actually gives you more qualitative data than what you typically get from a lab sample. So challenge with the lab sample is when you look at oil quality, when you take that sample, you're pretty much, as long as it's getting mixed, getting a good representation of that oil that you're sending off to the lab. The issue with wear debris, where you have components that are failing, they're starting to shed metal, get into the oil, especially as a filtration system on it, that gets filtered out pretty much as soon as it's generated. And so when you go to take that sample, it has to be producing that wear debris for you to even hope to get that in your little 4 ounces that you're sending out. And so because this now is always a sensor that's online, as long as we have a representative flow through the sensor, a portion of that pre-filtered in this case, because you have to definitely get the wear debris before the filter through, you always catch those. And so what we found with having literally now over 10,000 of these installed, wear debris happens in bursts. And it could be temperature changes in the equipment where you have some misalignment, could be the way the equipment is loaded. So not loaded the same continuously. If it's a bar of steel going through, that would cause some loading issues. And that's kind of when those events occur. A lot of the times you can't take samples when those events are occurring, obviously for safety purposes. So the times where you're generating most of that debris, typically a technician is not touching that equipment for good reasons, safety reasons. So this is just a data set from a bunch of industrial gearboxes. Looking at the lab sample. So on the left-hand side, it shows total iron concentration, iso cleanliness, kind of the worst readings they had over a 3-year period. Anything in blue is a reading from a known good gearbox. Anything in red is from a known failed gearbox. And these were borescoped, inspected, so we kind of knew exactly the state of all these equipment. And if you look at that, there's almost no way, if I took the colors off, that you could differentiate a good gearbox and a bad gearbox. And it's not because the lab's taking bad measurements. You're giving them only so much information that they can pull that information from. Whereas when you are online, one of these turbines up here in the top right-hand corner has has, as part of that data set, we had detected a fault fairly early, 2.5 years before it really got really bad. And we watched that over time get worse and worse and worse. And I'll go through the data and what it means in a second, but all of the lab data came back fine. In their situation, they would shut down the equipment and they probably wouldn't get to a sample. They'd do other maintenance as well. They probably wouldn't get to the oil sample for 30 minutes to an hour. So at that point, certainly everything's settled out. It hasn't produced debris in quite a while. Anything that was produced previously was already filtered out of the situation. So this is kind of an example where you actually get better data with this sort of sensor if you're looking to monitor failures within the piece of equipment. So again, a lot of you here because you're already doing vibration monitoring, you understand why online monitoring of equipment is important. So it's that same idea, right? Example on the right-hand side, when you start to have whatever that root cause is starting to cause a problem within equipment, it could be a contamination problem, water or something else. Catching that fairly quickly so you can take corrective action obviously is much better than the situation where you wait to take your oil sample. If you're doing it every 3 months or every month, it could operate for a pretty long time in that poor state of lubrication. And so being able to detect that earlier on important pieces of equipment allows for that obviously more active fixing of the solution. And again, I'll give you an example of some of that. But I think pretty much everyone here is pretty comfortable with why we do online monitoring within that. So this sensor, this is the wear debris sensor, the DM4500. This is what was the data set that I just showed you last time with the different pieces of equipment and the wear rate. It has a very similar value proposition as vibration. It's just a different set of data that is very comparable to each other. They pair together very well. So where vibration kind of lacks some information to make some judgment calls, wear debris does really good in that area. In areas where the wear debris is not great, let's say like isolating exactly where that fault would be, where vibration, we're going to tell you from the frequencies, it's a bearing pass frequency at this specific location. With wear debris, any component touching that oil, that debris is going to get in that oil and we're going to see the debris. We're absolutely going to see it from the sensor. We don't always know where it's coming from. So we're not always able to isolate where that is with wear debris. But the qualitative data you get to this on, again, usually more high valued pieces of equipment is extremely important. I said earlier that this is the best sensor on the market for what it does. It is by far. So our detection range is significantly smaller than anything else out there, other than an ISO cleanliness sensor, which is not useful for failure mechanisms outside of a specialty hydraulic system. So we detect on the ferrous debris down to 40 microns, so ferrous metals. On non-ferrous metals, we go down to 150 micron. So it's going to be metals only detection. It's not going to be sort of external contamination. It's going to be metals only, ferrous and non-ferrous. We're able to differentiate those. So as bits of debris passes through the sensor, we will identify if it's ferrous or non-ferrous, and then we will size that debris. So the raw data from the sensor before it kind of hits our Poseidon Live, where we do the analysis and that sort of thing, that's going to be particle size and counts in different bins.
What's the pressure rate?
150 PSI. Burst pressure is higher, but operational is 150. And temperature on this one, I think we put in specs. You guys remember 180? I guess it's around 180. Maybe Ryan will type it in there and pop up. Temperatures on the DM. We worked on some higher temperatures to get up to, let's say, safely run around 200 Fahrenheit.
Looking at operating parameters through this sensor as well, like GPM and things like that.
We estimate some flow rates, but it's not exact by any means. So we're really just getting wear debris. We're getting a board temperature, which kind of gives you a little bit of oil temperature, but that's not really super useful for any diagnostics. And we kind of estimate a flow rate, but again, it's not exact. So we're kind of taking an average of that. Its premise is to capture wear debris over time so we can do some calculations on it. That's predominantly what it is.
Steve, I've got a request from one customer.
Yeah.
Could you repeat the questions that are coming from the audience?
I did miss that one. Yeah. Yeah. So that question was, is there any operational information on top of the wear debris measurements? That was what the question was. So this is a good slide to understand what the sensor's doing. So I told you what the raw data was. That's the particle count by type. What we do is we take that data and we do some calculations on that so that we can turn that into something that's a little bit more useful to use from a reliability standpoint. So if you think about it again, vibrations detecting the vibration induced by the components failing, we're directly measuring the bits of metal that are coming off of that failing component. So we are actually directly measuring the damage being done on that piece of equipment. So as that bearing starts to fail, these are two bearings, that metal gets into the oil, that oil passes through our sensor. We're seeing, look, all right, based off of the size of the particles and classification, we actually turn that into a kind of an average mass loss over time. That's that red line that you see on that graph. And then the green is a total mass loss. And so now it's kind of turned just into a little bit of a physics discussion. How much metal can you lose on that bearing before it can't operate anymore? And so that depends on the size of the bearing, the application, a bunch of other factors that go into that. These are wind turbines. They tend to try to run these as long as they possibly can to get the most life. They're just trying to avoid splitting the gearbox and causing a giant mess of oil down the tower, while they order some of the largest cranes in the world to come in and do those replacements. So their business case may be a little different. In other applications is once you see that there's that problem, your next planned downtime, you'll do that replacement. So it's giving you that information that you then use within your particular application to make those decisions. But not all failures are the same, and that's important to know because that means they fail at different rates. You have different detection times, and how quickly that's getting into a potential catastrophic situation really depends on what's happening in that system. That top one is a bearing that was obviously very surface level for a long period of time. It was losing debris slowly until it got to a point where it started to lose those big chunks you can see right in the middle of that bearing. On this particular graph, we detected it fairly early. They went up, they took a look at it with the borescope, they saw the problem, it was verified, but it's not producing a lot of metal. So our feedback to them was it's operating, it's certainly failing, but it's not anywhere close to where you need to go get a crane in to do that replacement. So now you have this qualitative measurement of it's failing, it's failed, it's going down that route, but it's failing so slowly, you have plenty of time to go in and plan that. For them, they would like to replace multiple gearboxes at the same time with the crane that they just brought on site. So they're really looking to see how long they can get that top one. In case that bottom one were to pop up, they could then use that crane on two different gearboxes and save a lot of money from that. So this was kind of moving along. And then you can see as these blips get higher and higher, that's indicating it's failing faster. It's losing more material over the same given amount of time previously. So it's accelerating its fault. Again, very qualitative measurement to help decide how fast it's getting there. I believe, correct me if I'm wrong, no, Ryan's not in here, but we started to tell them it's getting bad right about here, but they like to continue to operate until that very, very end. So they got all the way up to our basically shutdown alarm, which is if you keep running it like this, your gearbox is going to split in half. So they got to that, and because we're directly measuring the damage being done, it's a little bit of a closed loop feedback to any changes you were to make to the equipment. So in their case, they can turn the equipment down so they're still operating, so still making power at that point, but they can do it at a safe level. So we use those as feedbacks so they can still operate the machine, but making sure that it's not going to catastrophically fail. So we had the example on the bottom. This was just a bad bearing. Material microstructure problem. Once it started to rip itself apart, there wasn't much you could do. The amplitude on this one here at the top is roughly the same level as the top one. So the shutdown alarms got to those rough same levels. This was 2 weeks, 0 to 100% fairly quickly. And then you can see where we use this feedback to say, okay, you derated it, but guess what? It's still producing too much debris to safely continue to operate. So they brought it back down again. To a level where they could continue to operate it until they could get the crane in, which was about 6 weeks from that. Yes.
So that
Yeah.
that change or a number there, that's just level.
Yeah. So just for everybody online, the question was, does the shutdown alarm and the alarming change with the application and the type of equipment? The answer is definitely yes. Jeremy can explain that a little bit more, but in general, the amount of oil flowing through, it's not the same. So in some applications we have a little bit higher, sometimes a little bit lower. That means we'll see more or less metal. So that'll change those applications. And then based off the type of equipment, it's again, that physics conversation, how much metal can it lose before you're going to do something. In wind, we're certainly a lot higher than most applications because that's big, bulky gearbox that can lose a lot more metal. Other applications you need to know a little bit earlier. So those do adjust. That's kind of a conversation with Jeremy's team on where we set those. We do have a lot of presets based off of our history of what we have, but then we'll run into a new piece of equipment we don't know a lot about. So we'll get more information and then adjust those thresholds accordingly.
So like you mentioned, there are certain scenarios where we try to extend that operation of that equipment until we can get to a place, whether it be a plant turnaround, whatever it may be. But so during that monitoring, do y'all ever make the recommendation, hey, if you're going to continue running this, at least change the oil? Because the more debris that gets in the oil, the faster the damage is going to progress, right?
Yeah, usually the question was, do we make any recommendations to continue to extend that until you can get to it? And certainly Jeremy's team kind of pokes around to see what you can do, because we're working with so many different industries. There's some stuff you can do, there's some stuff you can't do. So it's, well, what are the options? And then if you try that option again, right here, you can see, did it even make a difference? Did it make it worse? So you could do something and it made it worse. And other applications, I think, is just don't load the machine with as much as you had been doing previously. So it lowers the loads in the situation. So that is a little bit more of a back and forth with the operator of that equipment and Jeremy's team to kind of see what may or may not make a difference. Oil could certainly be one of those, especially if it's unfiltered. We have seen in some wind turbines where we just saw micro pitting starting to happen across the entire gearbox because the oil was being burnt up by the broken software that wasn't turning on the cooler. And obviously the fix was to fix the software, but the oil was so cooked that they needed to replace the oil as well. And that stopped the pitting from happening.
Great. One of the things that we offer is a magnetic filter downstream of our sensor. It'll pull things out of the oil, some micron size particle.
I was just thinking, special scenarios require some out of the box thinking.
Yep.
Sometimes we're too close to it to see some of that, right?
Yep.
So just wanted to, just question to see how y'all look at things and.
Yep. Yeah, when you get to especially those special case scenarios, when you get to that, there's a conversation that happens. There may be things certainly that you know about your equipment that we don't, and the levers that could be pulled to see what could improve things. And then obviously we have some history with equipment that we can think of some suggestions as well. But you are able to see exactly whether or not you are fixing it, making it better, whatever that is. And with vibration, you can maybe make the vibration go away, but if it's already starting to pit, it's always going to be there. You're always going to see that signature. Whether or not you've improved it or not is not within the wheelhouse of vibration typically. So they pair really well from a technology standpoint.
Well, we'll probably have some challenges like that because we do have some single point of failures where, we need to look for alternatives because the consequence of that is, especially 70, 80,000 barrels of oil a day. That's
right. Yeah, and those sort of single points of contact equipment, right? That's where you really see a lot of the value on the oil sensors. Where do those broken down pieces of equipment will cause you to stop the entire process? Okay. Any other questions on this before I transition to the other sensor? Okay. I like to use this as a transition slide. So this is one that has both sensors installed. So in some cases, we really always have a business case discussion with the end customer. What are the failure modes you're kind of looking for within that oil? What are you concerned about failing to determine what set of sensors you would use? So in this case, this was a single point of failure piece of equipment at a mine. Pressure gearbox, if that goes down, they can't process anymore. So they installed both sensors. We have what's called the FQMS, which is a boxed solution. So a lot of applications that are outdoors. We'll put them inside a NEMA 4 enclosure, which allows us to protect the sensors from flying rocks and debris and other things that can happen. So we have, again, a couple solutions that help do that. they had this installed, and I know nobody on the call and nobody in this room has technicians that would do anything wrong, but this particular technician decided to put an unsealed barrel of oil into the gearbox, which introduced quite a bit of water. And so nothing you could have prevented other than better training. They did have a oil clean room where they kept all their oil. This barrel of oil was not in the clean room, but they used it anyways. So I know absolutely nobody here would have this problem, but this particular customer did. And they'd introduced that water on this slide in this graph that you're seeing here. This red line is that wear debris 24-hour concentration I talked about, just kind of zoomed in from the slides that we saw previously. So you can see at some point our alarms absolutely triggered. It jumped up to a decent enough that we would reach out to the customer to say, hey, this was fine for a long period of time, and now it's not. So we had one data point, which is the gearbox is starting to be damaged. We had another data point, which was in green, and this is an output from our oil quality sensor, which is a relative humidity. So it's the saturated water within the oil. And it was hanging around 30%, which is pretty normal for this particular gearbox. It's outside. It is a lower temperature application, so it can only hold so much water. And all of a sudden, it railed all the way up to 100%. So another data point, which was that you have clearly a lot of water in the gearbox. So we knew now the root cause of the damage being done. If I had just given you a warning that something has happened, the wear debris is up higher, but it's not shutdown alarm, maybe you would go look at it, when somebody had some time. But we also knew immediately that there was water in the gearbox, and they knew that they had just visited the gearbox because they had just put the oil in. And so they were able to immediately understand, all right, something obviously happened that we need to go react right away. So they shut it down immediately. They put a dehydrator on it. Well, first they any of the settled water at the bottom of the sump they got out. They put a dehydrator on it to work the rest of it out, got the machine back up and running. So within about 30 minutes or so, they were able to shut it all down. Each one of these data points is about 10 minutes. So their reaction time was fairly quick. They got it shut down. And then when they kicked it back on, you can see they had to work most of that water out. Then the dehydrator worked its way all the way out, back down to what it normally would be. And so, they were able to basically say this gearbox, they would not have taken a sample or known that there was water in this, I think in their case, for another 2 months. That gearbox would not have lasted 2 months. So there was so much water in there, it absolutely was going to rip itself apart. And this is not something you typically would plan for, right? You wouldn't plan on a technician introducing a bunch of water into a piece of equipment, but it happens. On the flip side, a lot of equipment have seals, which is a barrier to like slurry mix or other sort of water or coolant, whatever that might be, and those seals can start to get bad. A slow leak would be the opposite of this. It'd be this graph. If you just flip it around the other way, you basically would have a slow increase of relative humidity. Obviously, that's more ideal because you can capture early, go find it and fix it before it causes damage, which it will eventually as it gets too much water in there. But you can actually see that problem, go hopefully fix that seal before it causes any problems and return it to service before it causes the damage. But in both cases, without the sensor, they certainly would have lost this gearbox because those events unfortunately do happen.
Question.
Yeah.
Some of our systems, blue systems, are NAS6 oil. No sensor, you look that close at it?
Great question for not me.
Not familiar with that kind of oil.
Well, it's what it is it's NAS6, meaning it's filtered to a NAS6. So
Oh, from a
or it has to be really, really clean for that system because of tolerances and all of that, right?
So yeah, that's a good question. So this is not looking at ISO cleanliness. We do use so our platform, we're able to integrate third-party sensors. That's how we got introduced to ITT Gold's iAlert, because we were introducing a third-party sensor at the time. So we have integrated an ISO cleanliness sensor, which will give you that output. So yes, we do that. It's not any of the sensors in this deck. It's a third-party sensor that integrates with the rest of the system, and we can report to you ISO cleanliness directly.
Okay. Yeah. On that same equipment, common lube oil sump for engine, gearbox, and generator, non-drive-in, drive-in bearing. So would that sensor mount in, like, say, a bearing drain?
Good
Because
question.
the oil going to the bearings is common,
Yep.
but the oil leaving the bearing, that's where you would want to see if there's any wear or breakdown.
Yeah, so the question was in some systems where you have a common lubrication point that lubricates multiple different pieces of equipment. If you use the common location, you don't know where it's coming from.
Right.
So typically, though, that's where you're going to do the ISO cleanliness, is just on the main. For wear debris or isolating where water is coming from, you'd have to be on the drain line of those equipment. So a lot of our steel plant applications, it'll be both the wear debris sensor and the oil quality sensor on the drain line so that we can detect the fault, particularly
Right.
with that piece of equipment.
So like, right now, commonly we take a whole.
Yep.
If it comes back good, then we know nothing's going
That's right.
on, right?
Yep.
But if it comes back bad, then we need to isolate
Right.
what is actually failed.
Yep.
And so, I was just thinking this would be a good solution for that.
Yeah, that's exactly what we do in a lot of applications where you want to isolate the detection.
Right.
It would just be on the outlet side of that equipment. We do that quite often. Yes,
Question from the field.
great.
Are these available for hazardous areas?
Yes. So the DM actually just got Class 1 Div 2 certification. So those are ready to go. And the oil quality sensor has been Class 1 Div 2 for over a year now. So both of these sensors are. The ISO cleanliness sensor, we can get Class 1 Div 2. So that is there. We do use like a viscosity sensor and some others. Those are not. We don't control that. So we can use some other sensors in there. But yeah, all of Poseidon sensors are Class 1 Div 2. So this is the oil quality sensor that was outputting the relative humidity. I picked the easiest one to understand to introduce and kind of transition to this one. Its actual main function is it's measuring the electrical properties of the oil. So I talked about that one trend line that we talked about previously. That really is the output of the electrical measurements that the sensor does. So while we do have relative humidity in there because it's a very good measurement, a lot of failures that we have to deal with, which is from water contaminating the oil. That's a direct measurement. The rest of the measurements that's happening in the sensor is indirect. So we're not directly measuring TAN, TBN, or whatever. Yes?
You mentioned these.
Correct. Yeah. So the question was if they're battery powered. They're not battery powered. They are wired. Yep. So the electrical measurements is actually the main piece behind what makes this sensor significantly different. So we've integrated relative humidity. It's a good case study behind it, but I will briefly show this slide. We're not going to dig into it, but just as conceptual to understand the core pieces behind it. We're looking at a bunch of different frequencies to measure impedance. Each one of those frequencies has been tested. You saw some of that test data that we had been working on previously with oil manufacturers, additive manufacturers, labs we worked with as well to kind of hone in on this for the past 20-ish years. So we're going to be looking for like free. So that example with the water getting in, we actually can see free water in our low frequency. It drops out because that little oil droplet will cause it to basically react very quickly. The middle frequencies is really a pretty spot on trend with oxidation nitration. One of our customers calls it the oxidation sensor and is almost primarily interested in this measurement that we take. And the high frequency is going to give you a little more of the dissolved and dispersed contaminants. So like on a engine, soot, that sort of thing is going to show up on this one. So we take all this raw data, again, which you don't need to quite understand at this point, into our platform. Jeremy's going to give you a little bit of demo of that, but then the Poseidon Live, this is an engine, a good example. We take all that data, we run it through our algorithms that we use for our monitoring in that platform. We give you back a health index. So the idea is that we can give you a 0 to 1 qualitative measurement of your oil. You can also have that graphed, which you see down here in the lower left-hand corner here. So you can kind of see how is that degrading over time? Is that slope changing? Is it jumping up? A lot of times you'll do a top off, the health index will pop back up. And then you kind of get an idea that you're kind of extending the life of that oil a little bit longer with those top offs. And then we're giving you hopefully what's a very useful red, yellow, green indication of oil health, as well as a red, yellow, green relative humidity measurement. And then it also has a direct temperature measurement of the oil. Most people already have that, but It's a measurement we take. It's in direct contact with that oil as one of those outputs. And then below that, you get into more of the detailed graphs. So you can see relative humidity graphs. You can see the oil health index. And then if you wanted to look at the more detailed impedance measurements, those are also down below in that screenshot. So that's all there. This brings out alerts and alarms. You can get mostly through email. So if you're signed up and you have that turned on, you get an email if any of those alerts hit. You can set up your own alarms and alerts if you wanted to. We do have text messaging. Typically, those are reserved for the emergency sort of alerts. Nobody wants to get a text message that my oil might be bad on 1,000 different pieces of equipment, right? That'd be too many. But some site operators want that higher level of emergency shutdown sort of indications that there are problems. But fairly similar to what you probably are used to with the iAlert platform. It's just tuned more towards oil and other sort of oil-based sensors that we've been using in the past. And then the one thing that kind of stands out and is different between all of this, and we'll break for lunch, is the FaroQ, which is an offline device that is more of a benchtop solution. So in a lot of cases, obviously with the wear debris sensor, oil flows. We can pass oil through that sensor. We get a very good indication of what's happening. Grease doesn't flow. It stays obviously where it's supposed to. And so a lot of our customers were needing to understand how much ferrous material is in that grease so they can then identify whether or not if that bearing particularly has a problem, for example. So this device allows you to use, it's usually mostly used for grease. It can be used for other media as well. So you could put almost any sort of media that's not metallic in a vial, drop it into the device, and it's going to give you an exact ppm. So you guys might be used to seeing, I forget what the metric has been so long. What's the PQ index? This is a replacement for that. Instead of getting a kind of a generic number that kind of trends over time, this is an exact measurement. Polaris Labs, some other labs are now trying to switch over to a direct ppm measurement, because if you can get an exact measurement, you probably should do that to move away from PQ. And this is the device that they are trying to move away with that. So this puts that capability there on site. So a lot of people are not doing grease analysis because most of the time they just want to know if there's a bunch of metal in it. And so taking a sample, sending it to a lab, you really have to have high expensive equipment to do that are greased. This brings that all on site. So you can take your own grease samples, you can drop it in, understand how much metal, ferrous metal is in there. So you then can make a decision on how do you want to act on that piece of equipment. Any questions on that? Good. Any online?
How many ounces of grease would you need to boost that?
It can take 2 milliliter, 5 milliliter, and then there's a grease thief. I can't remember how much that volume that is, but it's somewhere in between that 2 to 5. So small. You take like a big, almost like a straw amount, and you can put it in the device. Yeah. Yep.
Metal, we have to do.
And that's the beautiful piece, is that it has a carrying case. They can just bring it with them, set it up, take the samples, drop the sample in. It's 2 milliliters. You're talking just a small
I'll
amount.
give you some contact information, crane companies.
Cool. Awesome. That's a good application.
I'd rather them do that than me.
Yeah, yeah. Just for the comment on everyone online, talking about cranes, offshore cranes would potentially be a good application for this. But anything where you want to see that results, you need to see them quicker so you can take action. It's a pretty much a good one. And if whatever reason is you want to know more about what's happening on that grease, you can then send the sample into a lab to get that further detail on either the metal or the state of the grease itself. So Grease Thief is owned by a company that has a big grease lab. You can always send it into them and get some more detailed information of the quality of the grease. Maybe there's something happening that's causing the grease to go bad quicker that you would want to address to prevent future problems as well.